But at the instant time, what do I know for sure? This is still 2, but what's 6 miles, right? They're 6 miles apart, right? So you can look at this almost like a hypotenuse of that triangle is 6, right? Okay, let me keep going here. Let me keep going. What am I given? What do I want? Let me put what I want below this. What am I given? Are we given any speeds of anything? 600 miles per hour is the speed of the plane, right? But what is that in our picture? I don't see anything that we've labeled that shows that it's changing at 600 miles per hour. Remember, y'all had a little bit of trouble with this when we did this before spring break, figuring out what the 600 miles per hour is, like what variable is changing. So let's look at it this way. If you look at this plane as a point, that point's moving that way, right, at 600 miles per hour. Let's imagine, if you will, the distance from here to here. Let's call this distance x. All right? So straight down from the plane to the radar station, that distance, let's call it x. Would you agree that x is shrinking at 600 miles per hour? That's the rate at which it's shrinking. Because if this point moves, then that point moves. So as this moves over, this x gets smaller, and the rate at which it gets smaller is 600 miles per hour, because that's the speed of the plane, right? So in drawing that x, I can say that dx dt is positive or negative? Negative 600 miles per hour. That's how fast x is changing. See, I had to put that x in there, right? I had to see that x myself. What do I want to know? At the moment it's 6 miles. How fast is the angle, right? How fast is the angle? How fast? The speed of the angle. D theta, because we labeled theta over there, right? We want to know how fast is that angle changing with respect to time. That's what we want. What's d theta dt? And when do we want it? Because it's a specific moment. At, yeah, so at what though? At what is 6? We never labeled it, did we? Like 6 is this distance here, right? We never labeled it as a variable. So maybe we should label it. What do y'all want to call this distance from here to here? H, is that okay? H. So at the moment that H is 6. Do y'all see how I'm like constantly like going back and forth trying to like get my picture and assign variables, and there's no like cookie cutter always do this step, then this step, then this step. It's kind of like you're trying to take the word problem and create the math problem, right? So that takes some thought. I know what I'm given, I know what I want at the moment I want it. So I'm ready for an equation. Any equation you can think of that relates what things together? What do I have to connect here? What? X and theta. That's it. Give me any equation connecting x and theta together. Do y'all understand? I mean, this is kind of the bigger picture. You have to find an equation with x and theta, because when you differentiate it with respect to time, you need to get a dx dt and a d theta dt. You need both of these things to show up when you differentiate, right? We don't want dh dt showing up, do we? No, because I don't know anything about dh dt at all. So I'd like to keep h out of my equation if possible. So can anyone think of an equation that connects this and this together? Cosine. So cosine, what's the definition of cosine? Adjacent over hypotenuse. Ooh, hold on. So cosine of theta, let me write it down. This is not going to be our equation, but let's understand why. Cosine of theta, by definition, is the opposite, wait, is it? No. Adjacent over hypotenuse. So I could write x over h. That would connect theta and x together, but see, it has h in here. And you cannot fix h to be 6. Why can't you fix h to be 6? Can't do it till after the differentiation. So you'd have to differentiate this first. So you're going to have, in this, you would have a d theta dt, a dx dt, and a dh dt. All three of them would come out of this. So if we can, let's try and use something that doesn't include the h. Tangent? What do y'all think? What is tangent theta? Opposite over adjacent, right? See, and the 2 is 2, right? That's not a variable. That's always 2. So instead of this, let's use tangent. So I'm going to use tangent of theta. Now we kind of jumped to that. Tangent's 2 over x, right? We kind of jumped to that. Let me just remind you, though, we have to be looking at the general picture. And the reason we can do this trig is because this is a right triangle, right? So I can do this. Also, why not Pythagorean? Why not the Pythagorean like the previous problem? Yeah, you wouldn't have an angle in there, would you? You would have x squared plus 2 squared is h squared. Well, that doesn't have theta anywhere in it, right? So you don't want to use that. Good? All right, we have to differentiate this. Right? We have to do our implicit. Do you know what the derivative of tangent is? You should, right? I mean, that's the derivative of secant. No, it's secant squared, just secant squared. Just secant squared, yeah. Okay, so we should be able to take derivative of that, right? What about this side, though? This is a little bit weird. You don't do derivative top and bottom, please, right? No? You would have to do quotient rule, or you would have to bring the x up as an x to negative 1 and then do your power rule, right? Like there's a little bit involved here. So here's what I'm going to do. Instead of taking derivative right now, I'm going to do this. And then you just tell me what I did, and then maybe we can talk about why I did it. So what did I do here? I multiply both sides by x. Why do you think I did that? Multiply x here, goes away, x appears over here. Why do you think I did this?
You just moved it, so it's a product rule.
Yeah, so it's a product rule, and these two are both things I know derivatives of, right? So this is going to be kind of a cleaner derivative, in my opinion, than trying to do this. See, if I leave this like this is going to be 2x to the negative 1, and then when I take derivative, I've got to bring negative 1 out, this to the negative 2, then change, so I don't feel like doing that. I could do it, but I don't feel like it, so I'm just going to do this first. And now implicit. What am I differentiating with respect to? T again, right? Time. Most of the problems in this section you're going to be differentiating with respect to time because you're going to be talking about speeds, feet per second, miles per hour. So I take my derivative with respect to time on the left. That is a product. And then equals the derivative with respect to time on the right, and that's a constant. So let's do the right side first. I'm going to put it way over here. 0, right? Derivative constant 0. And then as it was pointed out, the left side will be a product, right? And so when we differentiate a product, we have to apply the product rule. The product rule says you take the derivative of the first one times the second one plus the derivative of the second one times the first one, right? That's the rule. So what is the derivative of the first one? Remember my story about me out the bar, the club? No? Asking that girl derivative of x, and she said with respect to what variable, right? What are we differentiating this x with respect to? T. So it's not 1, right? It's dx dt. The derivative of x with respect to t is dx dt. And that's actually good because that's what part of what we're given, right? So dx dt is the derivative of the first one times the second, no derivative. Plus, now the derivative of tangent of theta. What's derivative of tangent theta? Secant squared theta. But are you done? Are you done taking derivative? You have chain rule here, right? Derivative of tangent of something is secant squared of that something. You still have to take derivative of theta, don't you? The inside, the argument. What's the derivative of theta with respect to t? D theta dt. And see, we need that to show up, don't we? So d theta dt is the next part. And then now finish off the product rule, which is the x from the beginning. So if you're looking at this like old school f and g, this right here is f prime, this is g, plus this whole thing right here is g prime, and then f. That's your good old-fashioned product rule, but you also have to include the chain rule in this as well. Any questions on that? I don't think I want to erase that. I'm going to erase up here. No questions? Everybody's okay? All right, let's talk about what we know, like what we're happy to see here. Do we know dx dt? Do we know what that is? Yes, okay. Do we know what tangent of theta is? Well, we're allowed to look at this picture now, aren't we? Aren't we allowed to look at that picture? Yes? And this angle right here is theta, isn't it? That's theta. Tangent of theta is opposite over adjacent. Do you know the adjacent side right now? No? But could you know it? How could you know it? Pythagorean, right? Because we don't know this side, but we actually can fix this side to be 6. So let's call this side x, right? Let's call it x because that's what it was called over here. Let's solve for x in this one. This would be x squared using Pythagorean plus 2 squared equals 6 squared. So x squared equals, let's see, that's 36, that's 4, take away 4 from 36, you get 32. So x is root 32. Isn't it? Square root of 32. Just the positive. So now do you know what tangent theta is? It's this over that, right? This over square root of 32, right? That would be what that is. So we know tangent theta. Okay, secant squared theta. Remember, that means secant theta squared, right? That's what it means. Do you know what secant theta is? Well, secant's the reciprocal of what? Cosine. Do you know what cosine is? Adjacent over hypotenuse. So if I do adjacent over hypotenuse, that's cosine, right? So secant would be hypotenuse over adjacent. So do you know what that is? Yes? Could you square it? Yes? So we should be good with this. D theta dt is what we're looking for, so I'm happy to see that. And finally, do we know what x is at this moment in time? Yes, square root of 32. Okay, we're in business. Let's plug everything in and let's get an answer. Aren't these fun? No? So I think I'm sure I said this. There are 2 sections in Cal 1 that students do not like. The top 2, this is one of them. The other one is optimization, which comes later, because they're word problems as well. So anytime we do word problems, it becomes an issue, right? And then the math is actually, there's a lot going on here. But look, There are a lot of you sitting there, you want to be engineers, you want to be, you know, computer science. Like, you have to be able to think critically, you have to be able to think about problems, you know, put a lot of different ideas together, execute things without making mistakes. I mean, it's part of what you're trying to train your brain to be good at, right? I've never understood why a student would want to be an engineer and they hate math. It's like, you've got to enjoy what you're doing, right? Like, why would you want to not go do something that you don't like doing, right? Like, okay, all right, I'm going off. Let's continue. Start filling things in. dx dt was negative 600. All right, tangent theta, I've erased it, but it was 2 over root 32, right? I erased the triangle. Do I need the triangle back up here? Put it right here. 2 root 32 and 6, and that's theta, right? So tangent was that over that, and then plus secant squared. Secant was the reciprocal of cosine. So instead of this over that, it's that over that. So 6 over root 32, but we still have to square that. And then d theta dt, I leave that, d theta dt is d theta dt. And then times x, and x was root 32. And don't forget, the other side is equal 0, right? Our goal is to solve for d theta dt. I'm going to try and do as much of this as I can without a calculator, okay? So if I multiply here, I can just go across the top. That's negative 1200 over root 32. Plus, when I square this, I square the top, I square the bottom, I get 36 over 32. Right? Square the top, you get 36. Square the bottom, the root goes away. Times d theta dt times square root of 32 equals 0. I have a lot of options on what to do now. I could go to a calculator. I'm trying this without a calculator right now. I'm gonna clear this root 32 out. I'm gonna take the whole thing and multiply by root 32 here. And I'm doing this only because I see something that's gonna happen that's gonna be kind of nice. When I go here and here, watch. When I multiply this by root 32, the root 32s go away, don't they? That first one, and I'm just left with negative 1200. And the reason I wanted to do this is because when I go here, I can multiply it times that root 32, right? What happens when I hit root 32 with root 32? It just becomes 32. And you see that that's going to cancel with that 32. So those two multiply together. This becomes a 32, but then that cancels out with that 32. So I really just have 36 d theta dt. That was actually pretty nice, huh? And on this side, 0 times root 32 is just 0. I made all those roots go away, didn't I? Just with that one move. Now I'm going to add 1200 to both sides. And finally divide by 36. I don't think that goes in evenly, right? So 1200. Oh, 33.3. So d theta dt is 33.3 repeated. Anyone have questions on what I've got so far? Yes.
So 132, 136.
Okay, so when I multiply this root 32 on the left side, it had to distribute to both of these, yes? When I multiply times this second one over here, I multiplied it times this root 32. So what's root 32 times root 32? 32. And then that cancels with that 32 that's there. Is that what you're asking? Does that make sense then? Yes? Any other questions? What are my units? This is another tricky part of the problem. Theta and t. Well, t is measured how? In this problem, time was measured in what? Time.
Hours.
Hours. The only thing I have in here that has anything to do with time is miles per hour, right? So the assumption here was that time was always in hours. So this is going to be something per hour. Would it be radians or degrees, right? I mean, because it's an angle, right? Theta. So is it radians or degrees? It's always radians unless they specified somewhere in the problem degrees. Okay, it's always radians. So you could put rad for radians an hour. Remember, a radian is not the same as a degree from pre-cal, right? So if a plane is flying 600 miles per hour at 2 miles high over a radar station, then when the plane is exactly 6 miles from the radar station, the radar would have to be rotating at 33.3 radians per hour at that exact moment in order to be tracking the plane. An instant later, it's going to be different, right? Questions? Yes?
When you distributed the square root of 32, do you just not distribute it to the d theta over dt, or how do you do that?
Well, okay, so this is a good question. This is a real good question. Let me ask you a question before I answer this one. If I say to take the number 2, if I ask you to multiply 3 numbers together, right? 2 times 3 times 4. You don't do 2 times 3 and 2 times 4, right? You only do that if you had this, right? Then you would do 2 times 3, and then you would add to that 2 times 4. Okay, here, when you multiply 3 things together, you do these 2 together, which would be 6, and then times 4 is 24. Or you could have done this. These 2 together, which is 12, and then times 2, which is 24 as well, right? So with multiplication, it doesn't matter what order you do it, but you don't do a distribution. You don't do them all like 2 times 3 is 6, then 2 times 4 is 8, and then multiply those. My point is, you see we have these things, these 3 things being multiplied together? I'm now multiplying it by a 4th thing, right? So that 4th thing does not go to each one of these. It just goes to one of them. I get to choose which one it goes to. So I multiplied it times this one. Am I answering your question?
Yeah, no, I get it,
You sure?
Mm-hmm. Yeah, but it just kind of seemed like you were distributing it.
I did, because of this addition, I distributed here and here, right? So it had to go to this one, which when it went here, just canceled out. But when it went over here, I just applied it to this one. And since these don't have addition, these are multiplications, I just brought this down. Well, I canceled the 32 out. But I don't distribute to each one of these because there's not addition between these. Any other questions? The joy on their faces. I realize this is not great, but like I said, this is probably one of the most applicable ideas of the class. I mean, because you're actually looking at real physical situations. All right, which one? Street light. Oh, this is an interesting problem. I always want to skip it, but then when I think about it more, I think it's... Read the problem first. First thing, do you even see what's going on? Like, can you see things in motion here? Do you see a 20-foot light pole? Do you see a 6-foot man walking away from the pole? Do you see his shadow on the ground? Do you see it or not? I mean, everyone's going to be different here. I'm going to draw a picture first, just a rough picture. This isn't going to be my final picture. I'm just going to try and get an idea of what's going on. I've got a 20-foot pole here. Here's a light shining, right? I've got this 6-foot person, right? That's really running, probably not walking. 7 feet per second is pretty fast. Yeah, that's a speed walker. Okay, is that what you were looking at, like 7 feet per second? Yeah, that's pretty quick. It's more than that distance every second. That's probably a run, huh? All right, so there's the light, there's the person, and where's this person's shadow? To the right of him on the ground, right? I mean, you have to imagine the light's shining, right? The light that hits him gets blocked, and then his shadow is cast on the ground over here, right? So his shadow is like this on the ground, right? And you can kind of think of like the light rays that come over his head, that right there would correspond to the tip of his head on the shadow, right? Now he's moving this way, running, I guess, 7 feet per second. What does his shadow look like? Let's just imagine him down here, okay? Same person, same height, okay? Roughly same height there. Is his shadow longer or shorter now? Is his shadow longer or shorter now? Longer, right? His shadow is longer because the tip of his head now, the shadow has to be out here, doesn't it? So, I'm not drawing this to scale, but just to give you the idea, right? Like the shadow is longer, isn't it? And when he's over here, right? His shadow is really short, right? Just think, if a light's shining straight down, the only shadow you have is like your feet, right? If the light's just slightly off to the side, your shadow is going to be really small. If the light source is really far away, your shadow is going to be very long, right? So as he moves, right? As he moves at 7 feet per second this way, his shadow starts to get longer, right? And actually, the shadow moves away from him, right? Like if you were to say, relative to him looking at his shadow looks like it's just growing away from him, isn't it? Yes? Do y'all have questions? No? You all right? So what do we want to know? We know how fast he's moving. We know how tall he is. We know how tall that pole is. We want to know how fast his shadow is moving along the ground. So we need to all, I guess, agree what we mean is the tip of his shadow. Like here, the tip of his shadow you can look at as a point right there, right? Here, the tip of his shadow is a point right here. Here, the tip of his shadow is a point right here. So as he moves, that point moves, right? That point moves along the ground. And we want to know how fast that point's moving. How fast is that point moving relative to the pole? So like if you were standing here just at the pole watching this happen, how fast is that shadow moving away from you at exactly the moment he's 12 feet from the pole?
7.
What was that? What do y'all think? He's moving at 7 feet per second, right? Do you think his shadow is moving at 7 feet per second? No? You think how many of you think that his shadow is speeding up? That as he moves out, his shadow speeds up. Anyone think it speeds up? Yeah. Okay. Well, it's getting longer, right? So at every moment that shadow's further away than it was before, right? And then he moves a little bit, the shadow moved more than he moved, right? At least it appears that way. Anybody think that the shadow is slowing down? Like getting slower? As he moves to the right. I don't think that makes sense, right? To slow down, because then he would catch up with it, right? At some point. So his shadow has got to be moving at least at the speed he is, right? But if it's getting longer, it seems like it should be speeding up. Yeah. Well, let's figure it out. I'm going to erase this. This was just to get an idea. Do y'all want to see the animation? No, let's not do the animation. Let me try my general picture first. Okay, my general picture, got the ground, put G for general. Here's my pole. Okay, my pole is 20 feet. That doesn't change, right? 20 feet. I have my person, which is 6 feet. I'll do him in blue. Put 6 there. I'm just going to draw him as a stick with a dot on the top. My man. And I have a shadow, right, that's being cast onto the ground, and that's that point right there, right? And I want to know how fast that point is moving relative to the pole, right? To the pole. So I'm gonna call this distance from here to here, I'm going to call that S for shadow. I can call it X, but I'm going to call it S for shadow. Do you see how what I'm doing is I'm starting to set up what it is that I'm going to want? I want to know how fast S is growing, don't I? So I want ds dt. So that's why I labeled that S. Let's draw the instant in time. Same picture, 26, but here I know that the man is 12 feet from the pole, don't I? Right, at the instant in time the man is 12 feet from the pole. So this distance from here to here is 12. Do y'all agree? Is that S? Is this S? No, right? S is the distance from the pole to the tip of his shadow. This distance, 12, is not represented in this picture, is it? Which means I should probably represent it in this picture as a variable. How about we let it be the distance from the pole to the man? What would you like to call that? What? B? P. Okay? All right, so P is the distance from the pole to the man. S is the distance from the pole to the tip of the shadow. At the instant in time we're talking about, that P value is 12, isn't it? Let's start writing down some things. Given, I keep doing that. Given, what do I want? Someone want to give me either one of those? What you're given what you want? You're given 7 feet per second, right? That's a speed. That's the speed of what, though? It's the change in what? You have to look at this picture right here. What here is changing at 7 feet per second? From the man to the pole, which we are calling